Hey, this is Mr. Wells, and this is a little review of one-dimensional motion. So one-dimensional motion is really common. A sprinter going down a track, a ball dropping, um, a ball rolling down a ramp, cars going down the road, all are examples of one-dimensional motion. So in one-dimensional motion, if we want to study it, we have to be able to identify where things are first. So we use a reference frame, and we always use a number line as a reference frame. So we're going to use a number line, and it's going to be pretty simple. So now, if I have a person standing somewhere, then there we go. Now I can tell you where they are at according to this reference frame. We usually have the motion as horizontal, so we often call this x, and we need to define this, so I'm going to put the origin there and say that's 2 and 4 and 6. We usually have meters on there. So now we can identify where the person is at. And so we call that the person's position, where they are at. So the position is equal to 5 meters. Okay, we often say that use the position, we use the variable x, so we'll say x is equal to 5 meters. Okay, well that's great. So now we can tell where things are at on a number line. But physics isn't really interesting if things don't move. So if we have movement, then we're going to have changing position. So again, we're going to have our number line, and let's say that we have something like this. So I'll put my origin there, say -2, +2, 4, 6, and 8. And let's say that a person starts over here at 5, where they were before, and ends up some other spot, say over here at -2, at some later time. So we had some movement. Now we don't know how the person got from one place to the other, but we do know at the initial time, ti, and we don't really need an equal sign there, and here we have tf. So now we have an initial and a final. So the I and the F stand for initial and final, and we could write this as the initial position is equal to 5, and the final position is equal to -2. Now there's a special name we give to the idea of the change in position, and that is called displacement. And that's equal to the change in position. And we all know mathematically we can think of change in as delta, and so we can write that as delta x. And whenever we do that, whenever we do a change in, we always take the final minus the initial. So we could write that as x final position minus the initial position. So in this case, our displacement, delta x, would equal -2. And again, I should call that x, put some units on here. -2 meters minus the initial, which was 5 meters. So I get -7 meters. So that's important. That negative sign tells you the direction that they went. And so you can see the displacement is a vector. So it has a magnitude, that's the 7, so I know they moved 7 meters. And the negative sign tells you which direction they went in. And since it's a vector, I could also think of this in terms of an arrow. And let's see, I'm not sure which way that arrow is going to go. Is it going to go the right way? Of course I didn't pick the right way. So let me undo that and pick the other kind of arrow. And so that would be our displacement vector right there. So that would represent delta x. Like I said, the previous example did not tell us anything about how they got from one place to another. So let's say we have something a little more detailed. So we have a jogger that starts at a position of -3 and goes in the positive direction at a speed of 2 meters per second. So if I want to represent this, I'll draw my number line again. Now, as you can tell, my artistic abilities are not that strong. So one of the things that physicists do is we represent objects with just a dot. Sometimes we call this the particle model, because when we deal with this, the whole thing is staying together. We don't have to worry about the extendedness of the object. So if I look at this object here, let's say the origin is here, so I've got a -2, +2, 4, and 6. So I'm going to use a dot to represent the jogger at starting off at x equals -3, and it's moving in the positive direction, so that's to the right, and at a speed of 2 meters per second. So I'm going to end up, some people call this the strobe representation or a motion map. So I'm going to go each second where the object would be. So 1 second after that, the object would be right here, and 1 second after that, the jogger would be here, and so on. Hold on a minute, please. Can you close? So the object is there, and so on. So each second we represent this. Some people call this a motion map. And to kind of give you an idea, you can see positions, but you can't tell which way it was going, left or right or whatever. So we can often put on some velocity vectors, so I can represent the velocity that way. And what we notice is, since we have constant speed, the velocity vectors are the same size. And you'll notice that if something's moving at constant speed, then the dots are equally spaced. So, constant speed means you're covering equal distances in equal times. So I could also take this representation and I'll turn it into a chart. So I was at -3, then -1, +1, +3, +5. And from there I could also turn that into a graph, a position versus time graph. So anytime we graph, we should label things correctly with the units. And I need to extend my graph in the negative direction, don't I? So if I graph these points, we can see that we have there. Now my scale is not going to be perfect, but at 1 second we were at -1, at 2 seconds we're at +1, at 3 seconds we're up here at 3, at 4 seconds we're up here at 5. So I've got reasonably close to a straight line there. So we can also say that x is a function of t, so we can represent this as a motion map like this. We can represent it as a table of values. We can represent it as a graph. We can also represent it as a mathematical function. So in this case, we have a straight line with a slope of 2 and an intercept of -3. So I can say that x is equal to 2t minus 3. So the position can be written as a function of time. If the speed is not constant, then the motion map is going to look a little different. So I'm going to have a ball there, and then let's say it's rolling up the ramp, so it's going to slow down. So after 1 second, it's going to be there. As it slows down, well, after the next second, it's not going to cover quite as much ground, and in the next second, it's not going to cover as much ground, and it might end up here and be stopped. So if I draw my velocity vectors, I end up with something that looks like this. They're going to be getting smaller and smaller until they reach nothing. And then if I make a graph of that, hopefully you'll let me skip a step here. Specify that I'm going to change the coordinates, so x is going to be in this direction. So I've got t, we'll make that seconds, x in meters, and you get the idea. Let's say it starts off at 0, and 1, 2, 3, 4, 5, and so it covers a significant distance in the first second. Doesn't go quite as far in the next one, and so on. So this is going to just flatten out like that. So we're not going to write the equation in detail, but you get the idea. The other thing that brings up is when we have changing velocity, we say that the object is accelerating if the velocity is changing. So let's talk a little bit about acceleration here. So we have two cars that go from 0 to 60 miles per hour. So they're both changing velocity. They're increasing in their speed. And so they're both accelerating. But if we look at this, let's say that car 1 starts off at 0. After 1 second, it's going 10 miles per hour. Remember, this is velocity, not position here. Then it's going 20, and then 30, and then 40, and then 50, and 60. Okay. And let's say the other car starts off at 0, and then it goes to 2, then 7, 18, 30, 50, and 60. Okay. So they're both accelerating, but if we look at this, car number 2, the velocity changes by different amounts each second. So we call this non-uniform acceleration, which is actually pretty hard to deal with, so we rarely do. But if we look at this, the velocity is increasing by the same amount each second. We have the same change each second. So this is what we call uniform acceleration. And uniform acceleration, another good example, is a falling body and that velocity. So this, I would write this as the acceleration. Okay, it picks up 10 miles per hour of speed per second. So it's kind of weird. So acceleration is a rate of a rate, which we'll discuss in more detail some other time. But when you have uniform acceleration, there are some equations that are commonly used to solve problems where something is accelerating uniformly, and you're familiar with these. So I'm going to write them in two different forms. One form you may have seen is like the final velocity is equal to the initial velocity plus the acceleration times the time. So that's writing it with v's and f's. Other people write the final velocity as just v and the initial as v0. So this would be the velocity is equal to the initial velocity plus the acceleration times the time. They mean the same thing. You just need to pick whichever form that you like best. Okay. Another equation that you'll sometimes see is that d is equal to 1/2 the final velocity plus the initial velocity times the time. One really important thing is the d in that equation is displacement. It's not distance traveled necessarily. Sometimes those two things are the same, sometimes they're not. So you have to be very careful with that. In this form, it will often be written as the displacement, so the change in position x minus x0 is equal to 1/2 the final velocity plus the initial velocity times the time. Another equation is that, again, displacement, not distance, is equal to 1/2, let me start that one all over again. The displacement is equal to the initial velocity times the time plus 1/2 the acceleration times the time squared. And again, we can write this as x minus x0 equals v0t plus 1/2 at squared. And the final equation is the final velocity squared is equal to the initial velocity squared plus 2 times a times the displacement d. So in this form we'll have v squared is equal to v0 squared plus 2 times the acceleration times the displacement x minus x0. So you have to know that these equations are out there. You have to know when to use them, and that's for cases of uniform acceleration. And you have to make sure that you have all these things down, and remember that in this case d is equal to displacement. So hopefully that was a helpful review. Okay, and that's all for this review. Thanks.